Okay, how's everyone's heads this morning? Ready to give your brains some stretches with a bit of intrinsics, bit of maths. Let's get started and see if we can do this. All right, so this talk is somewhat of a sequel to a couple of previous ones I've done, looking at SIMD-based, like vector-based coding for audio algorithms. So there's a kind of general overview in my 2017 talk, and then last year was more specifically looking at oscillators, and then some of the theory of writing branch-free code. The ideas I'm presenting today, I think they are new and innovative. I've asked 2 domain experts and 2 large language models, and I didn't say to the LLM, "Oh, is this the best, most original thing?" Because it'll go, "Oh, of course it is. I've never seen anything as wonderful as this before." I was like, "Can you give me some research looking at these specific topics?" And it gave me a couple of fake citations and a couple of papers that talked about things that were vaguely related, but not really. So I think this is original. If any of you are more kind of math-minded and wanted to collaborate on a DAFX paper, reach out. Equally, if it's unoriginal and actually somebody's been doing this for 20 years, tell me about it in the Q&A. But I hope it's interesting regardless. So an AI declaration at the beginning, just because I talk to a lot of people about this stuff, and opinions range from "I'm using it for everything, it even feeds my cat," through to "burn it all down and destroy it forever and chuck the remains into the sun." So I'm talking about AI, not capitalism, or whatever. Yeah, I think the best thing we can do at the moment, while there is such a range of opinions, is just be honest and upfront about what we're using, how and where. So, sort of may contain nuts, that sort of thing. And so I have used it in this just for some of the mathematical research, just to help me out and explore topics and little branches of math that are slightly beyond my attention span. Other than that, it's not vibe coded or anything of that sort. So we're writing code without if statements or any of its friends, while loops, case statements, branches in flow control. Why would you want to do that? Well, when we think about the hardware resources that are available, and this is sort of what's inside one core of a modern CPU. We're talking here about kind of instruction by instruction level stuff rather than the sort of higher level multi-threading, multi-core. But what we can see is that you have these wide vector registers, Neon on the ARM chips, AVX and AVX 512 on Intel and AMD, which are processing between 4 and 16 floating point numbers in one operation. You then have parallel dispatch on the CPU as well. So, for example, this one, I think that's the inside of an M1. It's got 4 floating point multipliers, each of which are 4 floating point numbers wide. So you've got a sort of 16 wide machine there, if you can address all of that capability. And on the far side there, we have the instruction latencies or data dependencies, which is, because of the way CPUs are built now, if you start a multiply on clock 1, the result of that is not going to be available until perhaps clock 4. So there's a sort of internal latency to the CPU, but it can do more work in the meantime if you can find more work for it to do. And so the scope of this talk is really about writing oscillator code that can exploit these sort of properties of CPUs to get very high efficiency, and also, very importantly, sound good. So here you can kind of see you've got some operations ready. You start them at time 0, ready at time 3, and then the next lot are kind of interleaved with that. So on a typical ARM chip, you can basically do 48 operations every 3 clocks if you can line this up just so. On AVX 512, which is the latest and greatest on Intel and AMD, you can get 192 operations through in 3 clocks, and those can even be a kind of like a multiply and an add together. So you can do C equals A times B plus C or something, and that will that can all be done in one operation. There are some practical limitations with this approach because you only have so many registers on the chip. So if you think of each of these as a sort of logical data stream, there's 12 of them, and it's a little bit difficult to feed all of that with only 32 visible registers. So that can be a bit of a challenge. So I've already rejected one of the major concepts in programming, code flow. So let's slag off some DSP as well. BLEP, which is band limited steps oscillators. They suck. Why do they suck? Okay, because I'm going to have to justify that, right? I can't just go, yeah, they suck. They're branch intensive. They take a lot of if statements, a lot of flow control, and we've already said we're trying not to do flow control. Many of them require a lookup table. You can do it without, but typically the high quality band limited step oscillators, you need this lookup table, so you need some memory there. It's cache intensive, which is non-deterministic. You know, there are multiple layers of memory with different speeds, and if you're doing too many memory accesses, your performance will become unpredictable. You know, especially if you're a plugin in a DAW, like you might be a really good citizen with all this stuff, but then they might be running Contact as well, sorry, Simon, or any other big sampler, something big and memory intensive, and it will spam all the caches, and you kind of find that there's a lot of contention, a lot of memory access. And also with this type of algorithm, they're typically working forwards and backwards in time. So the sort of general method for these is you detect when the phase resets or when you need a step, and then you have to correct ahead of and after. So before and after that step point, you have to correct your waveform to make it band limited, which is both memory I/O intensive and just architecturally kind of really ugly that you have this oscillator that needs to keep some of its history around to fix that up after the fact. It's just, it's messy, it's memory bound, and computational load-wise, it varies by frequency, because if you have a higher frequency waveform or if you're doing kind of PWM oscillator sync, lots of modulation, you're going to have more of these transition points, and that's going to result in more of these branches and more of this kind of memory-bound I/O. So the performance of that oscillator will actually change depending on how you use it, which is just kind of annoying. It is unavoidable for certain oscillator designs. So just on a little bit of a tangent here, the one at the top there, that's the oscillator block from Cypher, one of the synths that I worked on for FXpansion and Rolly. And that needs an iterative design, basically because the oscillators can reset each other, but then resetting one can cause others to reset, which generate more resets. So you kind of, this particular design, you can't really do it any other way. You have to write those sort of branchy blep things. But when I set out on my own and started designing a new synth a couple of years ago, I decided I'm just going to design this with the grain of the architecture I'm using, and it's a kind of doctor it hurts if I do that sort of a scenario. Well, if the architecture doesn't lend itself well to certain things, then I'll just do different things, and it's nice just having the luxury of making those kind of choices of working with the grain of the materials I'm using. It's kind of feels like craftsmanship, which is a nice thing to do. So we're not using if statements, but there are things we can use to get things that behave like conditional control. We can use comparison instructions, greater than, equals, not equals, etc. You can produce binary, like bitwise masks with those that can be applied to most of your operations. We'll see that in the code example in a bit. And that gives you pretty fine-grained flow control in terms of values and in terms of data. So the idea is you're always executing the same code path, but you can kind of control how the data is influenced in different lanes as it passes through that same set of flows. It does mean like you're running all of the code all the time. So that is kind of the trade-off there, but it remains branch-free so that you can pipeline it. But that's kind of, it gives you enough flexibility so you can do phase resets on oscillators, you can do piecewise functions for windowing, And you can also do compile time evaluations, all the nice stuff we have in sort of C++, 17 and on with constex, brr, fixed size loops that get unrolled. You can use templates, so you can create different versions of the code for like, here's my 5 oscillator block and here's my 1 oscillator block, and just pass a different number as a template argument, and dispatch it, and that all works out quite nicely. So we're not as limited as we might think. So this is sort of the method, how this is all done, and this was kind of covered in my talk last year, so we'll sort of recap that and then see where we can get to in terms of improving it. So essentially, we compute a naive waveform. So in this case, it's a sawtooth. We all, I think, know those sound horrible. I'm not going to torture hungover people with naive sawtooth sweeps on a big system. That's not fair, and you all know what it sounds like anyway. And then using that naive waveform, we derive this piecewise linear window function. So that's basically min-max, clipping, scaling, that sort of thing. We then use some kind of shaping to approximate the error between the naive waveform and the ideal waveform, and then we subtract it to get something like this one, the last one here, which is a smoothed and hopefully band-limited sawtooth. This is completely branch-free. It's continuously evaluable, so basically for any value of phase, you can always compute all of it at any time. And the coefficients you need for generating these sort of windows and shaping, that can be pre-computed. So how far can you get with just that? So this is what I showed at the end of my 2024 talk. So at 2 times oversampled, it's a lot better than the naive waveform. The errors above 10 kilohertz are at minus 66 dB, which is, it's okay. It's a lot better than the naive one. Below 10 kilohertz, it's pretty good. Your dad or your granddad will think this waveform's fine. And at 4x, it's getting towards perfection, but I wanted to do better than this. So in that talk, I alluded to this idea that better polynomials would be available. So this one is just using a simple quadratic fit, and that's not a particularly good approximation really for that, for the sort of error correction that we need. I knew something better was available, but I hadn't actually implemented it yet. So then I went on a little bit of a quest to figure out what that should be. So that's just the recap method, looking at the waveform, generate a window function, shape it, and subtract it. But what are we really trying to do here? This is where we get into a little bit of DSP theory. So this is kind of the ideal band-limited waveform, and this will have no ripple or fade below your Nyquist frequency, no aliasing, and in this example, this one is probably I think that's a 6 partial sawtooth wave, so that will have 6 sine harmonics going up to Nyquist at 22, or if we had a 200 hertz like a bass waveform, that would have 110 of them. And the shape of this on the right here, we have this sync integral transition. So this is the integral of the sync function, and this is a perfectly band limited step that just gives you that kind of all the frequencies up to Nyquist and then cuts off hard at Nyquist, and is effectively mathematically equivalent to generating sawtooths with additive synthesis. So we can understand our error function, what we're trying to approximate, by basically subtracting that idealized waveform from the naive waveform, and that is the error that exists in any naive sawtooth wave. And that's why they sound horrible, because, I mean, you look at the sort of magnitude of those spikes, and remember that's going to be discretized, kind of sampled badly. So it's not surprising these things sound terrible, because there's just quite a lot of energy in that error signal. And obviously, the better we can approximate that, the more we can kind of smooth things out and get back towards the mathematical ideal. So that's what the rest of this talk is kind of looking at, trying to do. So looking at this error signal, the first sort of insight that I had was that, well, it's a real bugger to approximate something like this with polynomials, because it's got a sharp edge and then also a lot of wiggles, technical term there. But basically, a lot of the energy in this, a lot of the signal content is sinusoidal and up very close to Nyquist. So if you're at 2x oversampled, this bit of the error, like the high frequency content there, is effectively inaudible. And as long as we can approximate the main sort of distribution of the energy, that will be good enough at 2x and above. And so, yeah, I went around looking for different approximations, and landed on this after a bit of research and a few sessions with AIs and with Desmos and all sorts of different tools. But basically, we get to this idea that a logistic curve applied to these piecewise windows that I was generating before get a much better approximation of the energy distribution of that sync tail. So this is the kind of classic description of the logistic function. It's a sigmoid. It's actually a close cousin of the tanh function, which obviously sees a lot of use in audio. And we can use that like so. Basically, we've got the logistic curve. We use that to shape our piecewise window. And we can see that once the piecewise window has been shaped by that logistic curve, it's more or less a mirror image of our error there in terms of the sort of energy distribution. So if we subtract that from a naive waveform, and if we can do that continuously, then we should get, hopefully, a pretty nice result. Let's see. But we're trying to write performant code, we're trying to write efficient code, and there's a couple of problems in this formula. So this one is rewritten using powers of 2 rather than exponentials, but it's the shape of the curve is the same. It's just a slightly different scaling. But is that going to cause us some problems when we try and make this stuff run efficiently? Actually, it turns out it's not so bad. So we can get approximations for these. There are lots of recipes for these things, and you do, when you're using these types of approximations, you have to pay kind of close attention to the amounts of error on them. They are approximations. I think this that divide is probably accurate to sort of 14 or 15 bits, and the 2 to the x, I'm not sure, but again, I think that's round about sort of 16 or 18 bit level accuracy, and these sorts of things can execute pretty efficiently. So you can get this divide in sort of 3 to 5 operations, obviously all of which are parallel, and then the 2 to the x in round about 8. So what do we end up with? Well, something like this. I'm going to assume here that you have a preferred SIMD wrapper that is basically implementing vector types and gives you adds, multiplies. I think STD is going to be in C++26, which will do a lot of this stuff as a kind of first-class support in the language. Some languages already have that. I'm using my own class library for it, but there are many available. So what's this kind of doing step by step? Well, we've got phase increment, and then subtracting the floor, which basically when phase exceeds 1, that's going to produce a 1, which is then subtracted to reset the phase. We do some scaling to get the window, and then we calculate the denominator for the logistic, and then we do a division, subtract, and that's our signal out. That's our sawtooth wave. Can we do all of that in one clock cycle? Let's see. So if we put it into Compiler Explorer, which is a wonderful tool. If you're not using it, use it. It's fantastic for this kind of stuff. So this was Clang and set to compile for an AMD Zen5, so sort of latest-ish generation of CPU. This has got 29 instructions, but it's doing 16 voices with those 29 instructions, and we can, in theory, get 4 of these instructions out every clock with data interleaving on the Zen5. So, yeah, in theory, this should work even on a 256-bit. We should be able to get 32 voices through in 24 clock cycles, ideally, and with 512-bit. We should be able to do 64 voices in 24, but that's quite kind of theoretical, quite idealized. So we'll see how it works out in practice and talk about that. So more importantly, how does it sound? And the answer is, it's so clean that all of those, any artifacts you can see there, those are drawing artifacts in the scope there. This is cleaner than this FFT scope is able to represent without aliasing on its drawing code. So it is, it's clean to minus 130 dB. It sounds great. What's not to like? I was really impressed with that. I mean, we are 2x oversampled because we're sort of allowing for error close to the Nyquist frequency, but at 2x or at high sample rates, generally that's going to be way out of audible range. It's going to be 40K or higher, so we're just not going to worry about that because I don't make synthesizers for dogs. And how does it perform? This is sort of the moment of truth. So the first thing I tried it on was my kind of daily driver Windows machine, which is a Zen 2 from 2021. So this is a 256-bit, so it's an 8 wide, not a 16 wide. It's not the latest and greatest. Using Clang 21. Those are the results, and that is the real number that I got from the first test run. Now, if I was more of a showman, and if we weren't so kind of sensitive about copyright, I would be blasting Prodigy's Omen right now. You're all hungover. You know what it sounds like. You're just going to have to imagine that and hope nobody sues your brain for copyright infringement. But we've got the 32 voices through there for 1,000 samples in just under 32,000 cycles. It's very, very close, but just squeezing in on target there. So that's 0.98 clock cycles per sample per voice. The code's all public on GitHub, so you can have a look. You can try for yourself. So yeah, that was nice. But I thought I'd see how it does on a few other things as well. So if we go to 64 voices, you've got more, because we're interleaving more data. It squeezes a little bit more performance out, so you get just this kind of slightly more efficient, but it's only a very marginal difference, still basically the same. So then I went over to Compiler Explorer again. Now, I don't know when Compiler Explorer got this capability, but it can now run code. Like for a long time, you've been able to put C in, try it with different compilers, see what kind of assembly it generates. It can now actually execute the programs it's compiling. You don't get a lot of choice about what it's executing on. So it's running on, I think, their AWS tenants, and it kind of gives you what it gives you. On Windows, that seems to be mostly these Intel Ice Lake generation of Xeons, and on Linux, which is the default, it seems to typically give you something a little bit older. It doesn't work with Clang CL yet, the Clang driver for Windows. So effectively, if you want to run on Windows, you have to use the Microsoft compiler. If you want Clang you're going to be on Linux and you're going to get whatever machine they decide to give you there. We'll talk about that in a bit. But so this is an Intel machine from 2021 on Compiler Explorer and the Microsoft compiler. And it just missed, which is kind of annoying. 1.15, not far out. Maybe we can get it a little bit closer. So I dug into some of the CPU timing documentation to see what's going on. This is on this site here, agna.org. If you're interested in sort of low-level optimizations, this guy exhaustively documents the performance of all of the individual instructions on every generation of CPU. It's a delight. And what we can see here anyway is that there is this instruction with the catchy name of VRCP14PS, which is a 14-bit reciprocal, so it's 1 over x to 14 bits of accuracy. And if you're using the Z registers, which are the 512-bit ones, what we can kind of see here is that the Intel chip at the top it can do one of those every 2 clock cycles, and they take 6 to return a result. Whereas the newer AMD chip, they've invested some hardware resources in making that more efficient. That can do 2 of those every clock cycle, and they take 5 to return a result. So it's just a bit more efficient. And but I did realize that I was actually being more precise with this than I needed to be, because there are subtle differences between the 256 platform that I developed this on and the 512. So what we're doing on the left here, we take an approximate inverse. We do a Newton-Raphson step on that to bring it in more accurately, and then return that inverse times our numerator to do essentially a fast divide. AVX 512, this the kind of the fast reciprocal is already accurate to 14 bits, so we can actually leave out those Newton-Raphson steps, and that shaves off a tiny bit, such that if we go to 128 voices, we can get that Ice Lake machine sort of within target. Just about, although I did see a lot of variance when I was testing this out. So it's on Compiler Explorer. There's a share link later on in the talk. But I found that this particular machine, like the timings were quite variable, and I suspect that's because it's an AWS tenant. There's hyperthreading turned on, and so there are kind of other things competing for that core that makes the timing a bit less predictable. So then I thought we'll try one of the older machines that Compiler Explorer gives you on Linux. So this is a 2016 machine, and there's been sort of quite a lot of evolution in this part of CPUs over the last 10 years. And so you can see when you run it on an older machine, it works, but it's not. There just aren't the resources there to exploit with that kind of efficient code. It still can't go quite quick enough to meet the goal, but it's still pretty efficient, pretty reasonable. And then finally, a friend has got the latest generation AMD, which is an absolute monster of a machine. So the Zen5, which has 4 512-bit wide pipes for doing this stuff. And there we go. That's Michael Caine in my local park in Crystal Palace, saying you were only supposed to blow the bloody doors off, and it's a really impressive result there. Half a clock cycle, just above half, and I think with a bit more fine tuning and another couple of hours dicking about with compilers, I could probably get that down to the 0.5. So, this is kind of showing what the latest and greatest cores can do, just how much power they've got to process these kind of things. All right, so I'm going to consider that a win, but what else can we do with this? I mean, if you can make a sawtooth, you can make all of these other sorts of waveforms with a little bit more bookkeeping. So with two sawtooths, you can subtract one from another to get a pretty nice PWM waveform. We can do triangles by integrating squares or PWMs, or you can just generate triangles with window functions directly. And we can do hard sync with this technique, but you've then got kind of two oscillators. There's two different transition points. You have to kind of scale things to work out whether you're doing a kind of full range, high to low reset, or a half range, and kind of track what the last one was. So there's a bit more work involved, but it certainly can be done. And limitations. I mean, the main thing is we are kind of computing, or we can compute the value of any point in the waveform. And essentially what that means is that the window is always a fixed size and there's only ever one window for correction. So the problem with this is that the sync function sort of decays over infinite time. It's an infinitely long function, and it never goes completely to zero. So we are having to cut off at some point, and that is going to incur a little bit of an error. We could try and smooth that out. I haven't done so, but I find that if I can get that error to sort of 2 to the minus 20, basically you can do that in 20 samples. So as long as your waveform period is longer than 20 samples, it is all right. But that does have implications for how high this can go in frequency before you do start to get errors, which is basically a 20th of your sampling frequency. So at 2x, this will go up to about 4 kilohertz. I don't know why you'd want to listen to sawtooth waves that are higher than 4 kilohertz, but if you do, you'd have to figure out something slightly different for that. And under heavy FM, because we are pre-computing the sort of windowing coefficients for this transition, essentially if the frequency of the waveform is changing very, very quickly, there will be some inaccuracies in how we're generating it. But again, if you are FMing the crap out of sawtooth waves, you are not going to hear aliasing noise introduced by sort of small errors in window function coefficients. It's already going to be a very kind of bright and aggressive sound. So in practice, it's not really too much of a problem. So yeah, like I say, we have this sort of issue of the theoretical window going to infinity. We have to clamp it. We have to clamp it somewhere. Basically, if we get that to kind of 2 to the minus 19, 2 to the minus 20, then that little step function is down at minus 120, minus 130 dB. It's not gonna have any kind of perceptible or even perhaps measurable impact on audio quality. Okay, so why bother? We've got so much compute now. Why bother? Well, because we can. I mean, that's a good enough reason, right? But if we're building synths, 64 voices at 2x, 400 clock cycles is about 1% of one core. So it's basically quite nice. You can do a sort of like a 7-way super saw, 450 cycles, 64 voices, and still only be using 1%. I think efficiency still matters. When we're apparently burning the planet to build data centers everywhere, then I think if we're going to have all this silicon, we should at least make the best possible use out of it and aspire to be efficient and lean where we can. Is this the best way of doing this? I mean, there are other ways, right? With all this kind of compute available, we could look at other types of implementation to get these kind of waveforms. You could do additive. You could do these quadrature sine wave oscillators and just stack them up, and you'll get quite a lot of partials, quite a faithful waveform pretty efficiently there. You can also do some really nice things with FM and EQ if you've just got this much compute available. So yeah, I'm not saying that this technique is the be all and end all, but I had fun exploring it. I think it's original. It sounds good. It's pretty efficient, and it's just architecturally nice as well because everything sort of happens in one place in a small amount of clean code. Okay, so what's kind of coming next in the vector world? And it seems to be always nearly here. We've got SVE2 is the next generation on ARM chips, and that's here on some of the ARM chips, just not the ones people are typically using for music right now. And AVX 10.2, obligatory XKCD standards meme. There are all these different implementations. You have to kind of at least set up templates to compile for each one. So they're now both on ARM and Intel. They're unifying this definitely forever with one more standard. Okay, SVE2 is going to be it's going to be pretty nice, I think, but it's not here yet. I don't know why Apple haven't implemented this even on the M4. I suspect it's to do with sort of their optimizing for mobile devices and tablets and power efficiency, and this is kind of bigger, wider, chunkier silicon. But when it gets here, that will allow us to do similar things on Apple Silicon if and when. We should actually take a look. This code does run on Apple Silicon as it is now. Those are the results. So it's some way outside of the kind of the performance that I was targeting, and that's pretty much the same on the M1 and also the M4. They haven't really changed very much in the architecture over the 4 generations of desktop grade Apple Silicon. And the reason for this is it just hasn't got this sort of width of core. I mean, they have a lot of cores. They're incredibly energy efficient, so it's a kind of different set of trade-offs. But it just hasn't quite got the width on each core to do this at one clock cycle for say 16 or 32 voices. Eventually, I think at a point where they add that. We'll be able to get more performance from Apple's cores. I did notice, though, there's a discrepancy with this, even relative to the older Intel 2016 machine that I was testing on Compiler Explorer, and I did think that was worth investigating. That even this kind of pretty old 2016 Intel chip is managing 1.37, whereas the M1 is actually about 23% slower. Why is that? Basically, the Intel there is doing kind of 2 8-wide instructions at a time, and the Apple Silicon has to do 4 instructions that are only 4 wide. So it's kind of having to do twice as much work to get instructions into the core. And the Intel chips have a trick where move instructions on the actual kind of at the low level of the silicon, move assembler instructions are actually free in a lot of cases because of some deep, dark details of how these CPUs implement this stuff. And the Apple Neon Vector Unit doesn't have that trick, certainly on the M1, so it just pays a little bit of a performance penalty for that. And then, AVX 10.2, that's Intel's kind of new extension. I believe that's going to cap out at 512 bits, but it's kind of the idea is that they're going to sort of standardize it so that you can write the same instructions and it will run on all of the Intel cores. At the moment, you kind of have different levels on the server chips and the bigger, heavier chips and the mobile chips, and you have kind of like compile separate translation units for them, and this will eventually, when it reaches a critical mass in the market in about 5 or 10 years' time, that will hopefully make that go away. All right, reached the end of the talk. Few thank yous and acknowledgements for the various things I've used along the way. Agnafog and his instruction timings. It's so detailed, so nerdy. Somebody's done a similar one for the M1 as well, but that was less what I was focusing on this time round. Compiler Explorer, like I say, just brilliant. Desmos, wonderful graph plotting tool, and also anytime you're doing anything with AIs for code, you can always check. You always check with this to make sure they're not bullshitting you, because you'll catch them in a lie a lot of the time, and this just makes it nice and easy to do so before you're actually committing that to code and then wondering why the heck doesn't this work. Voxengo's spectrum analyzer there, used all the time. Sil, who's giving a talk later on for testing on his monster Zen5. And Daniel Lemire, who has written some useful tooling for benchmarking stuff running on Apple Silicon. All right. I appreciate there was a lot to get through. It's all on GitHub and on Open Compiler Explorer links if you want to try it out for yourself, or listen to it on your own speakers, or generally play around with it. Any questions?